Okay, thank you. So in this talk, Quentin and his collaborators will tell you about verifying real-world IPC, and in doing so, discovering bugs and optimizing codes in the production code.
Great. So my name is Noam Zilberstein, and I'm going to be talking about formally verifying microkernel interprocess communication at Meta. So as we all know, modern software is getting extraordinarily complicated, and we'd like to have better techniques for knowing whether it works. Luckily, verification toolchains are also improving, but there isn't that much evidence whether or not they're ready for industry use. So the goal of this project was to determine whether we could successfully apply formal verification in sort of a move fast engineering culture that you find in many large companies. And if so, what benefits would we achieve in the process? So Facebook or Meta is building this new operating system for sort of embedded virtual reality devices. And these devices have sort of fundamentally different constraints than things we've seen before. So if you're wearing some smart glasses on your face, the battery is going to have to be very small. The processor is going to have to be very small. So you need an operating system that is extremely lightweight and streamlined. And so this operating system is sort of based on a microkernel design where you have many individual components that communicate with each other using this inter-process communication. And you could say that the inter-process communication is the most crucial part of the operating system because if the components can't exchange messages properly, then nothing else is going to work at all. And so the way that this inter-process communication is implemented is using a series of concurrent, non-blocking, multi-producer, multi-consumer queues, and those are the target for verification. So again, we wanted to sort of answer this question, can formal verification be successfully applied in industry? And this use case was a very good fit, in part because it's easy to specify. We kind of know that these queues are supposed to behave like queues, so we can write down a specification for what they're supposed to do. The functionality is self-contained. We don't really care what's happening on either side. We just care that the messages get across properly. Oh no. It's high leverage because the entire correctness of the operating system relies on this one use case. And also the algorithm is not likely to change, in part because there was a lot of design work that went into it and it was patented. And now we kind of have this algorithm that we're going to use. So the strategy was to use an off-the-shelf proof system based on concurrent separation logic. Concurrent separation logic is sort of the state-of-the-art theory for reasoning about concurrent algorithms. So we wanted to use something that already had that encoded in it. We went with the Coq proof assistant and the Iris framework. And we wanted to really verify the algorithm, not the actual C implementation. And sort of, I'll get into what I mean by that in a second, but the rationale was that we had a limited amount of human brain power, and we wanted to use it on the most difficult problem, which is basically verifying the business logic, and non-blocking concurrency is already very complicated, so we didn't want to get into kind of verifying translations between C and sort of heaplang, which is the language we use within Iris. So the algorithm itself is very concise. It can be represented in about 24 lines of pseudocode. It's meant to be as simple and readable as possible. It only contains the core business logic, and it's unlikely to change much, which is good because every change to the algorithm requires updates to the proof. Meanwhile, the code is several thousand lines of C that uses all kinds of low-level optimizations to be as performant as possible. It changes frequently just from people adding new integrations and code mods, but no updates to the proof are needed. The correspondence between these two is kind of just certified by inspection, which is not ideal, but as I will explain, we already got a lot of benefits just by doing it this way. So the result was we proved the correctness of two different queues. One is called the generic queue, which kind of is used to exchange messages. And the ports queue is a variant of the generic queue, which also allows you to make reservations to guarantee that you'll have a slot. And in the process, we found some simplifications to the algorithm that improved performance a little bit. So we were able to eliminate an atomic load and a conditional check. And we also found a bug in some OS device driver initialization. So we were able to fix that as well. OK, I'm now going to get into a really quick primer on concurrent separation logic. So I think most of us here are familiar with Hoare logic. You can basically specify programs using preconditions and postconditions, and then use a program logic to prove these specifications. So for example, if you start with x being even and you have a program setting y equal to x plus 2, then you can prove that y is even. Separation logic is an assertion logic that you can use with Hoare logic that allows you to reason about resource usage, including the heap and concurrency. So we have this points to predicate where you can specify what values pointers are pointing to. So here we have x points to n. And the separating conjunction allows you to join these assertions by doing kind of local reasoning. So here we have p and separately q, meaning that p and q are both assertions that hold in disjoint regions of the heap. So if we have x points to n and separately y points to m, then we know that if we modify y, we won't affect x. Now, when you move to a concurrent setting, everything becomes a lot more complicated. So we can no longer prove this example about y being even, because after the program starts executing, some other thread may modify x. And then we don't know anything about its value. And to get around that, we use invariants. So invariants are kind of specified in these boxes to the left of the turnstile. And they're persistent assertions that are always true. So now we can prove this triple because we know that even if some other thread modifies the contents of x, it has to obey this invariant that the value is always even. But it also prevents us from doing some things. So if we wanted to atomically add 1 to x twice, we would not be able to do that because in between those two commands, some other thread may observe that x is odd. And putting this all together, we can specify concurrent data structures. So if we create this predicate q content that says the physical value of the q contains the elements in the logical list L, and this invariant, which kind of defines what it means to have a valid physical structure of the q, then the specification might look like, subject to the q invariant. If we start with a q containing the elements L, and we nqx, then we end up with a q that contains the elements of L with x appended to the end. And it's not quite this simple. We use logically atomic triples in reality, which was mentioned in the Q&A of the previous talk. But this is sort of the basic idea. OK, so let's get into a sketch of what the proof looks like. First, I'll talk about what the queue actually is. So the generic queue is a queue that's used to exchange messages in this OS kernel. It's based on a fixed size ring buffer, which means you have a fixed size array in memory, and the elements of the queue kind of wrap around in the buffer. All the operations are non-blocking, so we never acquire any locks. And the NQ and DQ happens in 2 phases, which means that instead of just getting elements in and out of the queue in one shot, you first kind of request a slot, and then you read or write the data on your own, and then you give the slot back. And since the previous talk was about the MPMC queue, which is also created by Meta, I'll talk a little bit about how they're different. So this queue is meant to be a little bit more streamlined. It doesn't have as many features. It's also implemented in pure C instead of C++, so it doesn't use like the fancy C++ features. And it also has this 2-phase NQ-DQ, which was important to the operating system use case. So this is what the code looks like. I mentioned it's implemented in about 24 lines. The NQ path and the DQ path are pretty similar, but we can just look at the NQ path for now. On lines 3 through 6, it's basically just reading a bunch of state. And then on line 7, it establishes that the slot we're looking at is open. On line 8, it does a compare and swap to kind of claim that slot, and then it returns the pointer to the data so that the user can then read the data. And then in mark ready, it basically just records that this slot is now owned by the consumer because it can be overwritten. And then DQ is very similar. But the interesting thing is that these two grayed out pieces, which were kind of initially in the implementation, were found to not be needed in the process of writing the proof. So unlike in the NQ path, you actually need less information in the DQ path in order to establish that the slot you're looking at is ready to be consumed. And because the conditional didn't need the owner value, we were able to eliminate the atomic load as well. Okay, so I mentioned that the data is stored in a ring buffer. The top diagram kind of shows what that looks like, where the Q values kind of wrap around. But reasoning about modular arithmetic is often very painful. So for the purposes of the proof, we kind of unfolded this ring buffer into an infinite ribbon, where now all the data is kind of sequential. And in addition to the data being sequential, now every slot is only used once. So for the purpose of the invariant, every slot in this ribbon kind of progresses through this monotonic progression from empty to free. And that allowed us to simplify a lot of things in the proof, because we know, if we know that we're going through this monotonic progression, if we ever observed kind of the state at one point in time, we knew it could only be further in the progression later on. And these states also tell us a lot more about the queue memory layout than just the value of the slot. So by putting this in the ribbon, in the invariant representation, we're able to kind of recreate what the entire memory layout of the queue should be. This is kind of a slice of what the invariant looks like. There's more, but this is kind of the basic idea of what it means to kind of specify the physical layout. So we have this pointer to the Q base, which we call Z. And we know that the producer counter will always be pointing to Z plus the capacity of the Q. So it's all the way at the end. That's the next slot that's going to be written into. And then the consumer counter is always pointing to Z plus the consumer index. So that's the next value to be read. And then for everything between the Q base and the producer counter, we specify kind of what data should be in that slot according to the ribbon state. Hold on. Ooh. Okay. So this is kind of literally a sketch of what the proof looks like. On the left, you see the code that we saw before, and on the right, there's kind of this state diagram. So each highlighted line in the code corresponds to some sort of memory update. On line 7, it's not really a memory update, but that's kind of where we establish that the slot we're looking at is in this empty state. And then on line 8, we do this compare and swap, which claims the slot for NQ. And so each of these transitions corresponds to kind of updating the invariant, because every time we update the memory, anytime we do a write into memory, we have to make sure that that obeys the invariant. And so you can go through the rest of the code and see kind of how the invariant updates. Okay, so in conclusion, this project is evidence that it is practical and useful to apply formal methods in an industrial setting. Not only were we able to prove the correctness of these queues, which kind of increases confidence in the project overall, but we were also able to improve the production code as a result. So that's really great. The proofs were completed relatively quickly. It took kind of person months, not years. And the ramp up on Iris was quite difficult. It's a very powerful framework. It has, all the underlying theory that we need, but it takes a while to learn. But the good news is that after you kind of ramp up on it, you can make progress a lot more quickly. So I mentioned we verified 2 queues, and we were able to complete the second proof much more quickly than the first. The reception within the company was quite good, especially after we were able to improve the production code. There are always people who don't completely understand the value of proofs, but everyone understands the value of finding bugs and simplifications. And then the message I kind of want to leave you with is that concurrent separation logic can make you a better programmer. I think that, maybe it's not feasible to verify everything, but I think just being aware of the ideas and how you would verify something can help you a lot. So in the process of doing this, it felt a little weird to me that we were sort of reverse engineering this invariant from the code. And it also sort of puzzled me, like, how did someone ever create this algorithm and make it correct without even having some sort of informal way of reasoning about what they were doing? So thinking about invariants could probably help you write correct concurrent code, even if you're not writing a formal proof. So that's all I have. I'm happy to take questions.
Thank you for a great talk. And there are wonderful questions here. The first question is that, how confident are you about the mismatch between the memory models, sequential consistency versus relapsed memory? Do the actual implementations only use SCXSS? Your simplification of removing an atomic load might make a difference.
Yeah, so it's true that the real, C memory model is relaxed memory. Our proof was sort of in a sequential model. It's possible that additional bugs showed up there. And in an ideal world, we would verify the actual code. We would use the right memory model, but part of the idea of this project was just to boost confidence in the result and figure out to what extent can we use formal methods in industry. So I think from that perspective, it was a success. And we were able to find issues in the implementation, even just with this sort of naive approach.
Okay, the next question is that, aside from human resources, are there impediments to actually verifying the C code, for example, using VST?
I think the hardest part would be the human part, which is that the people who work on the C code base don't want to have to worry about the proofs. And ideally, if you are verifying the actual code, you would want to sort of put it into continuous integration somehow, so that your proof wouldn't be out of date. And that would annoy a lot of people because they would go to make updates, they would see that some cock proofs started to fail, and they would have no idea what to do about it. So I think that's probably the biggest barrier. Given that the actual code is so much more complicated than sort of the algorithm, it would probably take a really long time to verify the actual code, but it's probably possible to do.
Jihoon, we have some local questions. I'm going to hand
Okay.
Hello. Is the unfolding from modular arithmetic to the virtually infinite queue done with proof or outside of your proof system?
Yeah, it's done with proof. So we have a few lemmas which kind of allow us to convert between these logical indices and physical indices. If you look sort of in the invariant, modular arithmetic does show up. Like when we're specifying the memory layout, we have to take mods. But it's nice that we were able to kind of contain the modular arithmetic just to the physical memory layout and not use it in kind of the logical pieces.
And one more Philly question.
You mentioned these logical states that abstract from the code, and they make you, obeying by them, make you a better programmer. Have you identified the exact same sequence in other data structures, or would that be a reasonable hope?
So you mean like this sequence? I think that each program probably follows its own progression. I mean, it's kind of interesting because you would probably always have this empty state, you would always have this free state, But depending on how the exact algorithm works, you have sort of these intermediate states, which the invariant needs to know about, but the user probably wouldn't know about. So one example is this owner set to cons, right? Because we do 2 updates right after each other in this mark ready function. So the user of this would never guess that there's this state owner set to cons, but it needs to appear here. And in the second queue that we verified, one of these states also didn't show up. So I think there probably is always some sort of progression like this, or usually there's some progression like this, but the exact states you have would probably be different.
Okay, back to you, Jihoon.
Thank you. There is one unanswered question. So is Meta planning to deploy Iris and more algorithms? What kind of algorithms and on what scale would Meta want to deploy full functional verification? That question is particularly interesting because we have 2 consecutive talks on verifying algorithms used at Meta. So, yep.
Yeah, so it's unclear. I think there is desire in some places to do it. I mean, I will note that the previous talk was code from Meta, but it wasn't done by Meta. So some other places where I think that full verification is sort of not on the table where you actually verify the code. But for some crucial sort of algorithms, there is sort of more and more desire. There are examples in the hack language of various kind of optimizations and features of the language that have been verified as well. It's not, though, super prolific yet, and there is a lot of cost to doing the verification, so it's not suitable for every use case.
I think we have a little bit of time for one more question. If no one is asking a question, I'd like to have a question. So you said in the beginning of the talk that this queue is non-blocking. So did you prove such a non-blocking nature of this queue?
It's not proven. So there are still places where sort of contention could happen even without the locks. And so you'll notice in the code that there's this while loop. So instead of waiting for a lock, you kind of just keep trying this routine until you succeed, because there's always a chance that the compare and swap will fail, and then you have to kind of get a new index and try again. So we did not prove anything related to that, related to basically how long you might have to wait in order to get an index.
Okay, thank you so much for your wonderful talk.